All right, welcome and thank you again for joining our bi-weekly webinar, Energy Storage at PNNL, where we share some of the research that's going on at the lab around energy storage and how that, especially in this case, how that is going to impact the new grid storage launch pad that is slated to open on campus towards the end of 2023 in there. As many of you may have heard over the course of these webinars, GSL is really focused on what are we going to need to do? What are the tools? What are the use cases that we're going to need to validate these next generation of energy storage technologies faster than we have in the past? If we're truly going to impact 2030, 2035 climate goals, those technologies can't take the development cycle that we've seen before. They need to go faster. A key part of that is understanding the degradation of systems, how to develop those models, and then how do we actually get in and accelerate our life predictions of these new technologies so we have a higher level of confidence they are going to work when they are deployed on the grid. And so I'm happy today to be joined by Qian Huang, who will be talking about some of our degradation analysis on lithium-ion batteries. So Dr. Qian Huang has over 15 years of experience in materials and process development for energy storage and conversion applications, such as lithium-ion batteries, redox flow batteries, and solar cells. Before joining PNNL in 2011, she worked at Dow Chemical with a focus on new products and large-scale application development. In industry, she achieved Six Sigma Green Belt Project Leader certification and acted as the Black Belt coach. Currently, her primary focus at PNNL is the investigation of reliability on energy storage systems and fundamental understanding of the degradation mechanisms of large-scale energy storage systems. Dr. Huang has authored or co-authored over 30 publications and holds 8 international patents, including 5 that have been issued. So with that, thank you very much. And Qian, we'll let you take it away. Thank you for joining us today.
Thank you so much for Vince's introduction. Let me share my screen first. Is that okay for the slide?
Yep, we are seeing the slide fine. Thank you.
Great. So good morning, everyone. Thanks so much for this opportunity to introduce our current work on lithium-ion battery degradation study, particularly by a calorimetric approach.
Qian, if I may interrupt, sorry for it. I forgot an important message to send, if you wouldn't mind. So please, as you're going through, there will be an opportunity for Q&A at the end. Please, any questions you may have into the chat window. Please don't do it in the Q&A window. Please put it in the chat for that. So Qian, I apologize for the interruption, but just realized I forgot to provide that guidance. Thank you.
Sure, no problem. So on this talk, I will cover the following several parts. The first is the background introduction, more related to lithium-ion battery, degradation mechanism of the battery, and the reliability testing for grid application in PNNL. The second part is our approach on the heat measurement, then followed by the detailed discussion by the case study. We will compare 2 different kinds of chemistry-based cell. And then we do more analysis on the sources of heat generation and followed by the summary and future work in the end. So let's get started. We all know the lithium-ion battery very well since we can see it actually everywhere. It can be considered as a big success in modern electrochemistry. So over the past 40 years, the pretty big progress have been made on lithium-ion battery. I think starting from the 1980s, the initial concept started, and then to the very successful commercialization in 1991, and followed by the application development starting from the small scale in portable electronic devices, and more recently in large scale for the transportation and the grid applications. So let's take a look at principles for the lithium-ion battery first, which actually cover two parts. The first part is the lithium-ion concept to replace the original lithium metal, which is achieved by using intercalation or insertion type of both cathode and anode to enable lithium-ion stored and transferred within two host structured electrodes. So that's why we call the lithium-ion battery also rocking chair battery. The cathode here, normally we use lithium metal oxide, and the anode, we use graphite or other carbonaceous materials. And on the other side, the second principle is more related to the interface. Specifically on the anode side, we call solid electrolyte interface, SEI. That is a passivating film formed by the electrolyte decomposition in the initial cycle on the surface of the anode to prevent the further decomposition of the electrolyte and enable high reversibility and the long life of a lithium-ion battery. This interface concept is pretty important for the lithium battery and also related to the degradation. We will talk about that a little bit later. So these two main principles are critical to make the lithium-ion battery commercialization come true and currently become the foundation for the lithium-ion battery industry. So based on this, the state-of-art lithium-ion battery now can achieve high energy density that is over 600 megawatts per liter and 250 meg-hour per kilogram, and high energy efficiency above 95%, as well as the long cycle life that is 3,000 cycles. So with all these advantages, the global lithium-ion battery sales volume has been dramatically increased in the last few years, and as shown here. And also in this trend is estimated to become more significant in the future, the coming few years. This is driven not only by the fast expanded the EV market, but also by the grid application. Its growth rate actually is even higher than that of the EV markets, as shown here. So specific for the grid application, actually there are a big range of battery chemistry show promise as shown here. But so far, 78% of the battery system used in grid service are lithium-ion battery, which dominate the grid in addition to the EV markets. So this is the background introduction for the lithium-ion battery. Then we move to the specific grid application. So in terms of grid surfaces, lithium-ion battery shows even higher flexibility, and that can cover a wide range of rated power and duration. So here actually show the paragraph is compared with the EV application. For the grid application, there are really pretty diverse types of grid service operation for battery energy storage system. But among of these, lithium battery dominate all the operations, so which shows a high flexibility. And here also show an example, actually a very successful example that demonstrates the world's largest lithium battery energy storage system of 100 megawatts delivered by Tesla to power over 30,000 homes in South Australia around 5 years ago. And it actually has been expanded by 50% in 2020. So towards the grade level application, lithium-ion battery showed a successful example and facing more opportunities, since so far it's still the most mature and competitive battery technology among the modern battery systems. But it's still facing a lot of the challenges. The top challenge here we show actually for the grade application is the cost, safety, and the reliability. So the cost topic has been discussed early in our webinar, and here we more focus on the reliability part. Since DOE released the grid energy storage strategy early and identified the validation of reliability and safety as one of the challenges for energy storage system. So this work we targeting to the reliability, and that actually is more related to the degradation part, as Vince mentioned earlier. So here, let's talk more details about reliability and the degradation of lithium-ion batteries. The battery degradation actually depends not only on component chemistry, but complex physical chemical processes during diverse operating conditions, such as the dynamic cycles, temperature or thermal effects, the time between operations, and other environmental factors. So the degradation is not a simple process. It's pretty complicated. And the accurately predicting this degradation process is not a simple task. But normally the degradation process can be grouped into two parts. First is the degradation at rest, we also called aging. And for this part of degradation, we normally use calendar life as the metrics to measure, and which actually most dominant by the temperature, state of charge, SOC, and the time. The second part of degradation is that during the operation, and we also use the cycle life to measure this part of that degradation. And the key factors are rate, depth of discharge, DOD, and heat. And all these factors are added to the static factors together. And furthermore, we here also show the various possible degradation mechanisms, which mainly cover three parts. The first part is most important on the interface, as we mentioned earlier. So during even at rest or operation, the interface will grow, and no matter on the anode side, we call the SEI, or the cathode side, we call the CER. The interface growth will lead to the internal resistance increase and lead to the capacity fading and the potential shift. This potential shifting will push to the higher voltage of the cathode and lead its grain cracking. The second part is the cathode part. The cathode particle degradation is most related to the overcharging, transition metal dissolution, and voltage change. And the cathode degradation is more related to the cathode material itself. For example, here, the nickel-rich layer cathode material show the more significant degradation than the lithium-ion phosphate-based cathode material. The last part is on the anode side, and this is mostly induced by the particle cracking and exfoliation, since the anode actually more reactive with the electrolyte. So this kind of degradation more related to the interface reaction. And based on all these degradation mechanisms, actually there one factor is pretty important and we cannot ignore it. That is the temperature heat. So the temperature heat play a critical role in the degradation, no matter at the rest or during the operation, as shown here. So in the following, we will take a close look at this thermal effect. And the thermal effect on the degradation can be summarized into three parts as shown here. The first part is more related to the interface. Actually, the interface such as SEI is very sensitive to the temperature. The higher temperature will accelerate the SEI layer cracking and the continuous SEI growth and make the interface thicker and thicker, leading to the internal resistance increase and capacity fading, as we mentioned and showed earlier. The second part is the electrolyte is very sensitive to temperature too, especially due to the lithium salt, lithium PF6. So at a high temperature, that will enhance the decomposition of lithium PF6, especially with like the chance of moisture that is contain proton impurity. The last part is the cathode part. So the temperature actually will thermally induce the crystallographic transformation of the cathode and the irreversible intercalation of lithium-ion will into the cathode lattices with the loss of capacity. So based on all these summary on the thermal effect on the degradation, we can easily understand that heat actually accelerates the degradation. But can we think in an opposite way? That is, will degradation go back to accelerate the heat generation and will be characterized by the heat measurements? So this actually is our main focus of study. So when we further to talk about the motivation and the initial work on the heat measurements, we need to briefly introduce the lithium-ion battery reliability testing for grid application in PNNL. This is a long-term program, and we tested different kind of larger scale commercial lithium-ion battery from different major battery manufacturers, and based on the standard protocols. These protocols actually developed by DOE program. And here is actually showed the detailed recorded data, such as this kind of grid surface include frequency regulation, peak shaving, and also show the detailed procedures here. I won't go to the details for this program, but one important and interesting phenomenon we found that when we put a thermocouple on the surface of the battery during operation, the battery shows quite different thermal behavior during diverse operating conditions. That indicates the thermal characteristics might be a critical factor for the reliability and the degradation of lithium-ion battery. So to pursue this thermal study, we developed an in-situ heat measurement approach. We use ARC, accelerating rate calorimetry, to measure the heat generation of commercial lithium-ion battery under fresh or degraded status during the operation. And then the thermal signal aligned with the electrochemical signal will be recorded and collected at the same time. And further, these signals will be analyzed and combined with other characterizations by comparing for these signals, finally to figure out the relationship between the heat and the degradation. During this process, I need to emphasize two more things. First is for the thermal measurement mode here. Traditionally, we normally use the isothermal mode to measure the heat. That is, provide a constant environmental temperature and with the heat exchange like a thermal chamber. But in this study, we will use the adiabatic mode. It is to measure the total heat release without any heat loss or exchange, so as to target the worst case. And another thing we need to mention is for the cells we are testing here, we use two kinds of large-scale commercial cell based on NCA and the LFP-based cathode material and the same graphite as the anode. And the degraded cells we use here are after more than 2 years peak shaving testing. So based on this approach, here is an example for the heat measurement in an adiabatic mode. And as we can see, the recorded thermal signal on the bottom align well with the electrochemical signal on the top during the charge and the discharge. So this demonstrates the adiabatic mode is an effective approach to investigate thermal behavior that is associated with the electrochemical performance of lithium-ion battery. So in the following, the thermal signal, as shown here, the temperature and the temperature change rate will be further transferred into the heat and the heat generation rate by using the specific heat capacity and the mass. So with that, we will go to the detailed discussion for first is the first case study that is based on the NCA cell. So as we know, NCA is a kind of nickel-rich cathode material, and it normally has 3 pairs of redox peaks, as shown here, corresponding to the phase transformation from the H1 to M, then H2, finally to H3 during the charge process, and the opposite way during the discharge process, as indicated in the CV and the voltage profile during the charge and discharge. And meanwhile, the heat signal actually align very well with this phase transformation process. And more specific, we can see the endothermic effect in the initial charging and also during the discharge phase M here. Another phenomenon is we can see the significant increase in the heat release near the end of discharge here. And another key point we learned from this case is when we increase the rate, from C/10 by C/3 finally to 1C, actually corresponding to the current increase. The heat release increase significantly, that more related to the irreversible heat in the cell. We will talk about that a little bit later. And based on that, we did more than 2 years peak shaving service for the cell. And after that, we did the heat measurement again. We can see the NCA cell showed a significant degradation of this long-term peak shaving service with around 16% capacity loss, and also shows the very big shifting for the voltage profile during the charge and the discharge, as well as the CV curve. And meanwhile, the degraded NCA cell showed much more heat release, no matter the total heat generation or heat generation rate. So this thermal effect is probably associated with the degradation of NCA cathode material, that is H3 phase loss indicated by the CV. So we cannot see the third pair of redox peaks at a high voltage. So this is the first case for the NCA cell. And we also can get some learning from this case study is more degradation actually lead to more heat generated. And then we move to the second case study that is based on the LFP lithium-ion phosphate cell. So the lithium-ion phosphate based cathode material normally show only one pair of redox couples here, corresponding to the iron 2+ and 3+ redox reaction during the lithiation and the delithiation. And according to that, actually we can see the multiple stage of the thermal behavior. And we also can see the endothermic effect in the initial charging, as well as at around 40% SOC during discharge. And we also can observe the exothermic effect near the end of discharge. And these two phenomena actually is quite similar to that in the NCA cell we discussed earlier. But one interesting phenomenon here is when we increase the rates, actually the current from C/10 to C/3, the heat did not increase significantly, especially during the discharge. This is actually quite different from the NCA cell. And this phenomenon probably related to the reversible heat, the entropy change of the battery. And we need to do more work for the mechanism study for this part. And same as the NCA cell, the LFP cell also under the more than 2 years peak shaving service. And we found after that service, the lithium-ion phosphate cell shows only 6% capacity loss, and with pretty consistent electrochemical signal, the voltage profile and the CV curve very close to the fresh cell. And the thermal signal here, actually on the degraded cell, showed a pretty similar behavior as the fresh cell too. It shows the similar and even less heat release than the fresh cell. And this thermal effect is associated with the relatively stable lithium-ion phosphate-based cell. So try to better understand the big difference. We put these two cells together at the same page, and also at the same peak shaving surfaces in the same scale. And we can, by this comparison, we can find after long-term peak shaving surface, the NCA cell showed a much more exothermic effect than the fresh cell, particularly in the beginning and the end of discharge, as circled here. While the LFP lithium-ion phosphate cell showed almost identical thermal behavior that is aligned with the electrochemical performance. So with that, we finish collecting the thermal data. So next stage, we need to combine with other characterizations and the heat analysis to figure out the mechanism. So first, try to better understand the big difference in the degradation level among these two chemistry-based cells. We did more electrochemical characterizations as shown here. We did CV, DVDQ, and ERS. And each characterization actually focus on different parts of the lithium battery. For example, the CV can provide more information on the cathode side, and the DVDQ more related to the graphite anode side, and the ERS more related to the internal resistance, including the ohmic resistance and the interface resistance. I won't go to details for this analysis, but the key learning from these characterization is that after long-term service here, the degradation of NCA cell is mostly from the lithium loss due to the cathode material, probably H3 phase loss indicated by the CV. And also the degradation on the graphite anode indicated by the shifting and the shape changing of DVDQ curve. The last is also indicated by the significantly increased internal resistance by the ERS measurement. And this internal resistance increase more related to the interface resistance increase indicated by the much larger diameter of the semicircle as shown here in the red curve versus the black curve. On the other hand, the lithium-ion phosphate cell did not show any degradation on the cathode material indicated by the consistent CV curves. No degradation on the graphite anode, although we can see the DVDQ curve shifting, but this is just the position shifting, not the shape change, indicating the graphite anode material did not change, just the lithium sources loss. The last part is the interface. Looks like the internal resistance and also including the interface keeps pretty consistent compared with the fresh cell after the long-term service. So based on this characterization, let's move to the last part. That is, we try to learn better about the sources of heat generation based on our data, thermal data. So in a lithium-ion battery, there are a couple different parts to contribute to the heat generation. And as shown here, they mostly have 4 parts of sources. The first part is the irreversible heat. That's from the ohmic and charge transfer losses this is more related to the internal resistance. The second part is the reversible heat. That is from the entropy change, a kind of thermodynamic parameters, and that potentially indicating the status of the active materials. And the third part is the heat due to side reaction. That is normally induced by the gas evolution, SEI formation, and the interface reactions. The last part is the heat of mixing from the lithium diffusion inside an electrode particles. But the last two parts, heat due to side reaction and heat of mixing, normally are not significant and can be neglected at a low temperature or at a low rate. So then the heat sources actually focus two parts, irreversible heat and the reversible heat. Then since we can focus on the heat sources on these two parts, we try to separate these two parts of heat sources. Here is our consideration. So during the charge or discharge, the total heat generation we measured previously actually include the both irreversible heat and the reversible heat. And then the irreversible heat during the charge and discharge process can consider as the same, especially at the low current and at the same current during the charge and the discharge, since this is actually in proportion to the current squared. And on the other part, the reversible heat can be considered as the opposite during the charge versus the discharge, since the electrochemical reaction is opposite during the charge and discharge. So based on this, so we can actually calculate the irreversible heat and the reversible heat according to these equations. So follow this approach and concept. Here is the detailed result for the separation of irreversible heat and the reversible heat at a low rate, C/10 over different SOC level. And we compare that for these two cells. The general idea we found is for the NCA cell, we can see for the irreversible heat curve, actually that value is much higher than the after degradation than the fresh cell. Since the irreversible heat more related to the internal resistance, so that means the degraded cell have the much higher internal resistance, probably related to interface growth as we learned from the CV curve. The other part is the reversible heat. We can see that curve actually shifting means the entropy change shifting. This part of the heat related to the active material degradation potentially. On the other side, we can see the lithium-ion phosphate-based cell, no matter the irreversible heat and the reversible heat, these curves are pretty consistent, which indicates after degradation, not the internal resistance increase or change, and nor the active material degradation. So based on this, we find our thermal data actually can interpret the degradation level or mechanism of lithium-ion battery. Actually, this is just the starting point of our study, not the end of the work. But we have to conclude based on our current work. That is, we found the degradation accelerates the heat generation and can be characterized by the heat measurements. And we developed the in-situ heat measurements and also compare the different chemistry-based commercial cell to validate this approach and these concepts. And we also successfully separation of the heat sources and can identify the more detailed mechanism of degradation based on these thermal data. Our future work will focus more degradation mechanism study, try to separate the cathode and the anode, since right now all our measurement is based on the full cell, but we try to measure the entropy change and then to accurately identify the reversible heat of full and half cells, and as well as do more characterizations of degraded electrode materials. And the last but is our ultimate goal is to use these heat data to help on the development and the calibration of our lithium-ion battery state of health modeling in great applications. So we really want to thank for the financial support from the DOE OE grade storage program, and also really appreciate the lot of help from all of my colleagues, especially for Day One, Alistair, Bruce, Nimat, Vish, David, and Vince for the lots of help. Thank you. So with that, I will be happy to take any questions. Thank you.
Thank you, Qian. Well, we'll get started with questions here. If any of the audience does have questions, again, feel free to put those in the chat and we will get those to you or get those answered. So we did have a few here that have come in. And again, part of it is looking at, I think there's a lot of interest in, once we understand the degradation, how does this feed back into our controls? You know, how do we control the batteries better so that we can, you know, limit degradation? So, you know, after looking at this, you know, within the battery management system, are there certain things that we could input in there to help control that? And one of the things I was looking at, like on your slide 11, you were showing in the NCA that the H2 phase going away at what, about 3.7 volts in there, 3.6. You know, just trying to look at it, is that a potential, you know, somewhere as you're developing the dispatch pattern for that, that should we try, if we have the option of avoiding going through that and generating heat, is that a reasonable assumption to be able to do that? Or?
Yeah, I think so. We can, based on the heat generation data, try to develop some control system based on that. And we can see actually heat generation is quite different at different SOC. And even we actually did before, the cathode or anode behave quite different during the charge and discharge. If we can do like the design system for example, sometimes the cathode showed more exothermic effect, but the anode side is the endothermic effect. We probably can take use of the heat from the cathode to make up for the anode side. I think there are a lot of space based on this heat measurement to think about. Yeah, I think so. Yeah.
Okay. And I had, there was just kind of a clarifying question, I guess, around the adiabatic versus constant temperature.
Mhm.
How, when you envision like these lithium ion cells going into a pack, is there, you know, I guess I view it as the adiabatic. Would that be more similar to a system that's maybe in the middle of the pack and doesn't have as much thermal management, whereas the constant temperature has an active, there's more active cooling of the system? Would that be a fair idea to kind of look at?
Yeah, that's a pretty good question. I think it's maybe even worst case without the battery management system, since it's still like maybe the isothermal process, the stators still, I think, have the heat exchange. And the adiabatic system is really worst case without any heat exchange. So that's, I think, the most extreme I think a case. We just do the worst case study, but we do compare these data. Looks also pretty consistent. For example, as showed page 11, we can see total heat generation here without any heat exchange. The heat is accumulated faster. So this, and we actually also can see the heat generation rate. It's changing, and compare with that. Actually, let me see if I can change it to my backup slides. We did like in a thermal, like in a chamber. This is a traditional isothermal. I think this is still without a battery management system, but should be more close to the real system. But we still can see the big difference, like the normal charging, discharging, when we compare with the different chemistry. So the degradation actually is more significant than we expected. So here it's still like a more, I think this is still the low rate charging or discharging, but the temperature will increase like over 2 degrees C compared with not significant the lithium-ion phosphate. So.
Okay. You know, as we look at lithium-ion chemistries, you know, there's been extensive testing on NCA and LFP. Where would you see, you know, some of the standard NMC compositions falling in here? You know, is it in between, do you think? Is this kind of the extremes that you've looked at here and NMC's in the middle, or do you have an idea on NMC?
I think NMC should be close to the NCA. If NMC is kind of nickel rich, if that's the nickel rich, it should be similar like the nickel rich, the NCA material. But I think that all also depends on the different vendor. But we find some case the NMC even degrade more than the NCA. So,
Okay.
yeah.
All right. And then one question came out on slide 17. We noticed in your DVDQ plot for the LFP, it was on the degraded samples, it's a very similar shape on your DVDQ, but there seems to be a shift in there. The reason for that shift, and then the shape of it almost exactly.
Yeah, the shifting most related the lithium loss, because we plot this as a function of the capacity. We can observe like 6% capacity loss for the degraded LFP cell. And that's why, based on this, we can see the capacity, not capacity, the DVDQ curve shifting, but the shape is the same. Yeah.
Okay, so it's the lithium loss that causes that shape because it's based on capacity.
Yeah, but the material itself didn't show any degradation. Since compared with that, the NCA, you can see the significant shape changing, shifting for the DQ. So
Okay. And then this was under that peak shaving. That was a 4-hour peak shaving application.
I think so. Yeah, I think so. Yeah, we keep the consistent with our reliability testing protocol.
Yeah. So in comparison, the other one we typically test to is frequency regulation, which is a application.
Yeah, we also did that as well. So based on our initial data, we show like the peak shaving degraded more on the cell size, on the different cell. So we choose the peak shaving as the case study, since they show more significant degradation compared with the frequency regulation. Yeah, we did both, and both showed pretty consistent results.
Okay. So the energy intensive applications tend to, you think, show more degradation than the higher power.
Yeah.
Okay. So I'm curious about where that takes us, because we're seeing this focus now across the industry to move towards longer duration systems. I think, we've seen lithium-ion, where a 4-hour lithium-ion system is fairly much a standard product. But as we look out, we're looking at, wanting, DOE's got objectives around a 10-hour plus storage systems, all the way up to 100-hour systems, even seasonal. What would, I guess, what do you think your impacts, and where do you see, in your opinion, lithium-ion being able to go for those longer duration applications?
Yeah, I think that's a very, very good question for the future of a lithium battery, especially for the grid application. I think right now, still lithium-ion battery dominant the grid application based on the data, like 78% battery system. But for the duration, I think that long duration, that's we are facing a lot of challenge. Yeah, the most used right now, I think, is 4 hours or below. Since the definition for the long duration, we need a discharge like 10 hours or more at rated power. So this is pretty challenging. I think the most challenge is for the cost part. Since for the EV market, the customer can afford the high cost for the EV, right? But for the grid application, we need like expand the size 10 times 100, even 1,000 size as the EV. The cost become the significant, I think, factors to dominate the future of lithium-ion battery, and also the material available, since like the nickel, cobalt, this material is not really show the much available, since it need to use not only EV market, but also grid if we adopt that part of material. Yeah, I think lithium-ion battery can achieve more than 10 hours, just the cost, safety, and kind of the degradation, the reliability, as we show here. These are the challenges. If really we can have the breakthrough or some maybe approach to separate the power and energy, I think that still have the potential, but so far, I think for the long duration, they are facing more challenges.
Okay. Yeah, so in your testing, we've got two basic chemistries. But I mean, have there been results from like, different developers of technologies? Do we have the kind of samples across people that make different LFPs or NCAs? And is the data you've shown fairly consistent across those different vendors?
Okay, yeah, they are still have the difference from different vendor, but so far we use, for example, LFP and the NCA. That's from the largest, most dominant lithium battery manufacturer, and we haven't done any comparison among different vendors in a systematical study. And right in this phase, we just do more comparison among different chemistry, but that can be our future work to compare the same chemistry among different vendors. I think there exists the difference, the variation.
Okay. Well, Qian, I thank you very much for your time today and giving us an update on this. Looking forward to seeing continued work on this. We all realize that, understanding and then ultimately being able to take our understanding of the degradation and feed that back into our controls. So, can we dispatch these batteries smarter so we can get longer life out of them? In addition to just improving the materials, it is an active area where, there needs to be emphasis and there's a dramatic payback from being able to do that. So thank you very much for sharing those results today.
Thank you, Vince.
All right, and I'd like to remind everyone of our upcoming webinars as we close out here. If we can bring up that slide. So November 17th, Witness Martin and Yang Liang will be talking about high throughput experimentation for accelerated energy materials research that we're doing here. And then on December 1st, Jeremy Twitchell, who leads our regulatory storage program here at PNNL, will be talking about energy storage as a transmission and dual use asset. So please join us for those webinars. And if you have any questions on there, feel free to reach out to the PNNL at the email address in the link, or to myself or Qian directly, and we can get those answers to you as soon as we can. So there will be a recording of this. If you want to go back and review, please do that. And once again, thank you for your time and see you in 2 weeks. Take care.